All right, so are there any questions or concerns before we get going this morning? Okay. All right, so yesterday, right, we started section 3.3, right, zeros and factors of polynomial functions. We learned about the fundamental theorem of algebra. And I guess the main point is that every polynomial function of degree n greater than 0 has exactly n zeros. And some of those zeros may be complex numbers. Okay. So, given that, we started reviewing complex numbers yesterday. So we did page 2. Right? We did example 4, where we multiplied two complex numbers, right, in A and B. And now we'll pick it up on page 3 of your notes. That's where we ended, multiplying two complex numbers yesterday. Now we're going to do division of two complex numbers. So this is page 3. If you got the handout or you downloaded it to your laptop. And so I just want to emphasize what it's saying in here about the complex conjugate of the complex number z. Right? So z is a complex number. And complex numbers are written in the form of a plus bi, where a and b are real numbers, and I is the imaginary unit, square root of -1. And you know how to find the conjugate of a plus b. The conjugate a plus b is a minus b. So the conjugate of the complex number a plus bi, you just change the plus sign to a minus sign. Okay? And you have a minus bi is the conjugate. So z is the complex number a plus bi. We denote the conjugate of z with z bar. Okay? So z bar is equal to a minus bi. Okay? So to find the conjugate of a complex number, you just change the sign from addition to subtraction, or from subtraction to addition. And you need that in order to do the division of two complex numbers. So in example 5, we're going to divide the complex number 2 plus 3i by the complex number 4 minus 2i. Okay? And to carry out that division, what we're actually going to do is multiply top and bottom by the conjugate of the denominator. And that gets rid of the I in the denominator. So we have 2 plus 3i times the conjugate of the denominator is 4 plus 2i. Okay? So all I did was multiply our original fraction by 1, right? 4 plus 2i divided 4 plus 2i is 1. But the 1 that I used, right, is the conjugate, right? I'm multiplying top and bottom by the conjugate of the denominator over here, which is 4 plus 2i. And now I got to multiply these two complex numbers in the numerator, these two complex numbers in the denominator. We know how to do that from yesterday's lecture. You got a FOIL, right? So in the numerator, right, we multiply first terms. If 2 times 4 is 8. Then we multiply outer terms. We have 2 times 2i is 4i. And then you do the inner terms. 3i times 4 is 12i. And then you do the last terms. 3i times 2i is 6i squared. And then in the denominator, this is actually going to end up as a difference of squares, right? This is of the form a minus b times a plus b, which is equal to a squared minus b squared, okay? This is actually going to write as a minus 3 times a plus b, where a is 4 and b is 2i, okay? But we can carry it out just for kicks and giggles, right? We'll FOIL for kicks and giggles. We multiply first terms. 4 times 4 is 16. Multiply outer terms. 4 times 2i is 8i. And then when we do the inner terms, we have minus 2i times 4, which is minus 8i. So you see how the outer and the inner cancel, right? They go away. That's why it's called, you end up with a squared minus b squared. A squared is 16. B squared is going to be 2i squared. Okay? Then when we do last, we have minus 2i times 2i, which is minus 4i squared. Okay? With time, you'll learn not to just recognize this is going to be a squared minus b squared, and you don't have to carry out everything that I did here. All right, so simplify the numerator. We have 8 plus 16i, right? 4i plus 12i is 69. And then I squared, you got to remember, is equal to minus 1. And in the denominator, we have 16. 8i minus 8i is 0. And then we have minus 4i squared, or again, I squared is equal to negative 1. So you notice the I disappears in the denominator. Okay. And so the numerator simplifies to 6 times minus 1 is negative 6. Negative 6 plus 8 is 2. So the numerator simplifies to 2 plus 16i. And the denominator, minus 4 times minus 1 is plus 4. 16 and 4 make 20. Now it says to write the result in standard form. Okay? So we got to split this up. And one thing on exam 2, division does not undo addition. A lot of people keep forgetting that. So you got to divide each of these terms by 20. So we have 2 over 20 plus 16i over 20. 2 over 20 reduces to 1/10. And 16 over 20 reduces to 4/5. And so 2 plus 3i, the complex number 2 plus 3i, divided by the complex number 4 minus 2i, is equal to the complex number 1/10 plus 4/5 i. Any questions on that, ladies and gentlemen? Okay. So in example 6, we're given the quadratic equation 3x squared minus 2x plus 5 is equal to 0, right? Quadratic equation of one variable. 3x squared minus 2x plus 5 is equal to 0. Does that factor with real numbers or whole numbers? No. Okay. So how are we going to find the values of x to make the left-hand side equal to 0? Quadratic what? Formula, right? Remember the quadratic formula? So a is equal to 3 in this case. B is equal to -2. and c is equal to 5, right? This is ax squared plus bx plus c form. So you know the formula. X is equal to negative b plus or minus the square root b squared minus 4 times a times c over 2a. So we do substitution. Negative b is a negative of negative 2. And then under the radical, b squared is negative 2 squared minus 4 times a, which is 3, times c, which is 5. And then that's divided by 2 times a, which is 2 times 3. All right. Somebody about to say something.
No, never mind. I didn't see the negative in front of the negative 2 at first.
Oh, okay. So we have a negative, maybe I could write that a little better. We have a negative of negative 2. And now you gotta simplify, okay? Negative 2 is plus 2. Negative 2 squared is 4. And minus 4 times 3 times 5 is minus 60. And 2 times 3 in the denominator is 6. So we have 2 plus or minus the square root of minus 56 over 6, right? So this is called the determinant, what goes under the radical, and it's negative, right? So our two values of x that make the left-hand side equal 0 are going to be complex numbers. Okay. All right, so now you got to reduce negative square root of negative 56, okay? So you got to look for factors of 56 that are perfect squares. So you know 56 can be written as 4 times 14. So let me write that out for you real quickly. 2 plus or minus the square root of minus 1 times 4 times 14 over 6. Okay? Square root of minus 1 is I. Square root of 4 is 2. You can't reduce the square root of 14. So this is equal to 2 plus or minus 2i times the square root of 14 over 6. Again, division does not undo addition and subtraction, does it? So we got to split that up and write that as 2 over 6 plus or minus 2i times the square root of 14 over 6. And now you got to simplify those two fractions. Oop, what did I do wrong? It's interesting. I made a mistake in my notes. It's amazing how you do that sometimes. Okay? So 2 over 6 reduces to 1/3. So we have x is equal to 1/3 plus or minus, and then we got 2 over 6, right, which is reduces to 1/3. So we have, how do I want to write this? Square root of 14 over 3 times I. make a mistake. Okay. I'm glad I caught it. Alright, so I made notes, I did not make a mistake on the board. So, what are the two values of x that make the left-hand side here equal to 0? Right, use the plus sign first, and you get x is equal to 1/3 plus square root of 14 over 3i, and x equals 1/3 minus square root of 14 over 3i, right? Use the plus sign and minus sign. So it says solve the given equation and give complete factorization. So this is half of the solution, right? These are the two values of x that make the left-hand side equal 0. Now we got to give the complete factorization. Yes, ma'am?
Would it be incorrect if you wrote it all in, like, as one fraction? Like 1 plus I on the square root of 14 over 3?
Well, technically, we want to understand, we're going to write out complete factorization.
Okay.
So you need to split them up in order to write out the complete factorization. Okay. If all you were asked is to find the solutions to that equation, you can probably stop right here. But to write out the complete factorization, you got to split them up. Okay. All right. So the complete factorization of 3x squared minus 2x plus 5 is equal to the leading term here, or the leading coefficient 3, times x minus the first 0, which is 1/3 plus square root of 14 over 3i. So, I'm going to maybe make things simple. I'm going to replace this left parentheses with left bracket, so we're not nesting parentheses, but we'll have parentheses inside brackets. And we have x minus, in parentheses, 1/3 plus the square root of 14 over 3i. Right? That's the first factor. And then the second factor is x minus the second 0. 1/3 minus the square root of 14 over 3i. Okay? You know how when we factor quadratic, sometimes we have x minus 5 times x minus 2? Well, instead of 5 and 2, we got complex numbers. Okay? Now, to complete, now we got to distribute the minus sign inside the parentheses. So we have 3x squared minus 2x plus 5 is equal to 3. Remember, 3 is the leading coefficient. Times, I'm going to drop the brackets and go to the parentheses. When I distribute that minus sign inside, I have x minus 1/3 minus the square root of 14 over 3i. And then when I distribute the minus sign over here, I have x minus 1/3 plus the square root of 14 over 3i. This is the complete factorization of this quadratic here, 3x squared minus 2x plus 5. Okay. So instead of having whole numbers, right, x minus a 5, right, a whole number like 5, and x minus a whole number like 2, same strategy, okay, the same process as with real numbers. It's just messier because you're using complex numbers. Yes, ma'am.
So you use the minus because the 1/3 is positive, so you're still like flipping the sign for the zeros?
Basically, right? If we use the complex, so let's say we solve a quadratic equation, and we got x is equal to 2, and x is equal to 5, right? Then what that says is the factors of the quadratic equation are x minus 2 and x minus 5, right? And so you're right? You're subtracting the solution from x, right? When you write it out as factor. Okay? So you're doing the same thing here. Okay. All right. Any questions on that, ladies and gentlemen? Okay. So let's go back to the top of page 2, and this is a good opportunity to talk now about the complete factorization theorem. Okay? So we have a polynomial function of degree n greater than 0, right? So here's the unfactored form of our polynomial function from back in section 3.1, page 1, right? You know that a sub n times x n is the leading term. N is the degree of the polynomial, and a sub n is called the leading coefficient, okay? And you know this term here determines the end behavior in the graph of the polynomial function, right? Does the right end go up or down? Does the left end go up or down? Well, all polynomial functions can be factored, and so a polynomial degree n greater than 0 can be factored in, can be written with n factors, okay? So that's what this is saying right here. F of x can be written as a product of n linear factors, right? X minus c1, c1, c2, cn are all real numbers. Okay. You got c1 times x minus c2, and so forth. And that's kind of what we did with this example over here. This is a polynomial of degree 2, and we wrote it with a product of 2 linear factors. Okay. And so an a sub n here, right, is the leading coefficient from our unfactored polynomial. Okay. So we're going to be doing more complete factorization of polynomials. Okay. And that's what this stands for using. If you have a polynomial of degree 5, it can be rewritten as a product of 5 linear factors. Each one is x minus some number. All right. Any questions on that? You want to take a quiz?
Yes.
Let's do it. Get a jump on the weekend.